Computer programs have been traditionally represented as a stream of characters. Intentional programs are represented not as text, but as a database. Not a database about the program, but a database that is the program itself. The key to the new representation is the concept of identity. In text-based systems, identity is a complex idea implemented by the use of names and scopes. It is easy to use a search command to find all occurrences of any given name, but which of these are definitions and which are uses? More importantly, which definition corresponds to any given use? These questions can be answered only by manual analysis, which is both painstaking and error-prone. In the IP database, all definitions have unique identities, and all references are resolved using this unique identity. Names can still appear, but they serve only to display the underlying unique relationship. This is the IP system displaying a program that is represented as a database. The advantages of having a unique identity for each reference are immediately apparent. When we select any reference, we can always find its definition by a simple command. For example, this K is a reference to this definition of a global variable. Surfing back to the reference, we check out another K, which turns out to be a constant. It is also easy to highlight the references for a quick overview. If the multiple use of the name K bothers us, we can simply and safely change the name in the definition, for example, to number of variants. Once the definition is changed, all references will immediately reflect the change. Because the names are separate from the means of storing identity, renamings or name conflicts that are incidental to code sharing cannot create errors. To enter a reference, I can simply type the name. If the name has been used by several definitions in the same scope, a list of possibilities will appear from which I can select the one I meant. Since the name is just a property of a definition, there is no reason why a definition couldn't have more than one name. In addition to the common name, we could have longer and more descriptive names for easier maintenance. Or if the project is international, we could have a translated name in the national alphabet displayed in Unicode. Alternatively, names could be automatically generated by the system using a consistent type-based naming convention. In IP, the concepts of identity and definition extend to all elements of a program, not only to operands. This means that I can select if and find its definition where we see the names and parameters for methods that display if and implement if. Or I can select the plus operator and go to its definition. The same thing is true for the integer type, and really for everything else that forms the program. This is the secret of the extensibility and flexibility of IP. Every part of a program points to its definition, where we can describe how the feature should look and how it should be implemented. The list of how-to methods is extensible. Many other aspects of a feature can also be modified or enhanced, for example, for editing, debugging, browsing, and source control. We call this concept the active source. My system has been loaded with the definitions for the features of the C language, so that the workings of this IP should look familiar. Just as we could change names earlier, we can switch to a different display method for showing statement lists, and then the display of the program will change, for example, to follow the formatting conventions established by Kernighan and Ritchie. We need not be confined to text syntax to show elements of programs. For instance, we can continue changing the display method for lists to show them as boxes. Or we can change the display for the conditional expression to show it as a mathematical formula. A pretty extreme format change shows explicitly how the same program is organized as a database. It resembles a parse tree of a compiler, and for this reason, we call it the IP tree. We've seen how the programs are represented as an IP tree of identified nodes, but this representation also means that the programs have to be edited differently from plain old text. Let's see how this is done. I can enter a simple expression such as st=1 just by typing it. My entry is divided into tokens. The tokens are looked up to find definitions as we have seen before, and the appropriate nodes are created in the tree. Program entry is modeless so that the few errors that might occur do not interrupt me. Instead, squiggly lines appear at the suspect place like in Microsoft Word's spell check feature. If I click on the error, I can see the error message in full. If I choose to do nothing about it, I can come back to it later using an automatic to-do list. Suppose I need to double the result of this addition. I can select the plus and the tree below it to indicate that I intend to operate on it. Now if I enter times 2, it will apply to what was selected. This is shown by the appearance of the parentheses. Let's undo this edit to see how we could double just k. We select k, then enter the same commands, times 2, and the result appears without parentheses to show that only k is multiplied. Editing statements is also simple. To insert an if statement, I select the place of insertion, then enter if. Replacement works the expected way. If I select a portion of the program for replacement, it will be replaced by what is entered. When large systems have tens of thousands of name definitions, IP's ability to browse by the syllables can be very useful. I can just type the start of several syllables of a name in any order until I find the desired API call. What is more, when the call is inserted, the edit time methods of the definition are activated so that the API can help with default arguments and intelligent prompts. In this case, not only the local window handle was automatically defaulted, but helpful prompts were filled in for the other parameters as well. One more nice thing about the editing in IP is that it works equally well no matter how the program is displayed. For example, let's change the display into a circuit format. Operators that have the capability now display themselves in terms of logic symbols and signal lines. It is still very natural to select one input of this AND gate and enter the usual exclamation point for negation. We see the inverter symbol right away. Changing back into C notation, we see the same operation in traditional format as an exclamation point.
Don't you dislike having to give the same information many times? This happens so often when we deal with any bureaucracy.
Look at all this information in a procedure header. Most of it is repeated in the interface declaration. As for most bureaucratic rules, there are good reasons for this duplication. The parameters are part of the interface, so they have to be there, but they are referenced from the procedure body, so it is nice to have them near there too. IP resolves such quandaries by storing the information in just one place. The primary information can be automatically imaged by the system in multiple places. In this case, if we change the interface definition, the procedure header will immediately reflect the change. This simplifies coding and eliminates a common source for errors.
The database metaphor for programs supports collaborative work very well.
Every edit is a transaction on a virtual copy of the program source that is called a version. The status of the various versions can be displayed at any workstation. All the old versions can be recreated by the undoing or redoing of the appropriate transactions. To illustrate the power of transaction-based intentional source control, let's rename a procedure and move it to a new place. Now let us check in the results. In IP, this is perfectly safe. In a text-based system, even a modest reorganization such as this would cause source control headaches and possibly errors when my coworkers synchronize with it. No wonder that conventional software becomes brittle and disorganized with age. It would be just too hard to reorganize it. Meanwhile, Paul, unaware of my change, continues his work. Not having synchronized with my check-in, he still knows the procedure by its old name at its old place. He can use the old name, and he can also edit the procedure right where it is. When his work is complete, he must merge as usual with the latest checked-in version before he may check in. The merging creates no conflicts. The code now reflects both my changes of the name and place for the procedure, as well as Paul's changes.